Okay, I think we are ready to start. I actually noticed that on one of the lectures, I gave a little bit misleading information about hyperbolic isometries. So let me start with the remark about isometries. Remark on, okay, on isometries of hyperbolic type. So we consider an F in isometry from HD to HD, where the fixed point set of F on the boundary consists of precisely 2 points. And in this, in this lecture, I started considering a special case, but then I somehow switched to the general case, but I forgot that I switched to the general case. So let me be more precise in this. So we consider the hyperboloid model. So we live in the hyperboloid model. And in general, F is, so it can be, the matrix of F can be written like that. In general, we can change, right? We can change a basis. A basis in the Minkowski space of signature D1 such that our D1 is decomposed into the direct sum U plus U orthogonal, where U is spanned by these two vectors P and Q. So geometrically, I have this, right? I chose 2 points, P and Q. And this is definitely two-dimensional plane. And this is my hyperboloid here. And in this basis, so such that RD1 is this, and let me write it this way, and the matrix of F. So I will just write it, the matrix of F on this basis. The basis is following. It has two-dimensional block E to some number, I don't know, mu, E to minus mu, 0, 0. And here I have the matrix A from the orthogonal group of order D minus 1. And this is 0 and 0, right? So this is a hyperbolic isometry. A special case is a hyperbolic translation. So special case I discussed in that lecture, that I mean. A special case is the hyperbolic translation along a geodesic. Translation along geodesic. And this is, by definition, such an F. So this is an isometry that is conjugate to the homothety or dilation that is conjugate to a homothety, or it is also sometimes called dilation in the upper half space model. Dilation. So this is, okay, let me denote by x to lambda x in the upper half space model UD, where the coordinate xd is just positive. So let me draw the picture. And this dilation is a translation along the vertical. So this is the origin, right? This is my axis xd. So this is a geodesic. So this is a homothety. So basically this point is mapped to, right? So if it is 1, then the next point is lambda and so on. So the orbit of this point belongs to this ray from 0 to infinity. If lambda is not equal to 1, but we can assume that lambda is greater than 1. And then this is the expanding homothety, right? Expanding dilation. And the attracting fixed point is infinity and 0. So my geodesic, so this is a translation along which axis? Along the half line the origin infinity, but I mean, so this is given by equations that x1 is equal to, and so on, xd minus 1 is equal to 0, right? Yeah, is this correct? Yeah. So the hyperbolic translations are quite specific, right? The orbits of hyperbolic translations are simply the rays in the upper half space model, right? So for every point, its orbit is on the ray. So if I start with x, then I'm getting lambda x, lambda squared of x, and so on, right? But generally, a hyperbolic isometry allows, allows some rotation around this axis. So generally, my orbit can be quite wild. It can jump from between different rays, right? So it can be first here, then here, and here, and so on. Yeah. So you understand it's quite different. As hyperbolic translation is quite a concrete isometry. So it preserves the hyperbolic metric. It's quite nice. And in the hyperboloid model, it corresponds to the identity matrix here. So for hyperbolic translations, A is equals to the identity. I somehow accidentally said that it is true, that it should be identity for every hyperbolic isometry, but I meant this special example. So for some clarity, I do this. Okay, this is, yeah, so let me fix this here. So for this translation, let me highlight it that here, A is the diagonal matrix. So it's the identity diagonal matrix. Yeah. Okay. It is an interesting remark that for this isometry, the orbit converges to infinity, right? So we see the limit point on the boundary. The group generated by this isometry is discrete itself. The orbit are just the orbit right, is discrete set on the line. The distances here are pairwise equal, but, and actually this is true for every orbit. Actually two interesting observations. If I take this point, then the orbit converges to infinity. If I take any other point, x, its orbit will also converge to infinity along some different ray. Yeah. Okay. In fact, for parabolic translations or parabolic, like pure parabolic isometries, we have something similar. In the upper half space model, the parabolic isometry, a parabolic translation is just a translation in the horizontal sphere. So this parabolic translation preserves infinity. And if, say, I take z to z plus 1 isometry, right, then the orbit, say, of the point, I don't know, I, will give you I plus 1, I plus 2, and so on. The limit is also infinity, right? It also converges to infinity. So for parabolic translations, we have accumulation points, the center of the whole sphere. Yeah. Okay, now I'm going to focus on discrete groups again. So it was a remark on quite an old lecture. Well, okay, not very old. So let's get back to discrete groups. I'm going to discuss a general question on how to, so we discussed last time how to construct a fundamental convex polyhedron for a discrete isometry group, right? So I just remind that we know that the Dirichlet domain D of P, which was the intersection for all gamma that are not actually, I also forgot to write it right there in the previous lecture, that the intersection should be taken for all non-identity elements. So for all non-identity elements from my discrete group gamma and H gamma of P, where H gamma of P is a half space. So it is a half space defined as follows. We have a set of X such that the distance between the point X and P is less than or equal to the distance between X and gamma P. So the Dirichlet domain is a generalized convex polyhedron. So it is a generalized fundamental convex polyhedron for a discrete group gamma. Polyhedron for a discrete group gamma of isometries in the space X. And geometrically, the picture is like that. I chose P with the trivial stabilizer. Gamma P is the identity. And for every gamma, I'm taking gamma P. I should find the geodesic segment, and I take this hyperplane, and the half space on the left side is H gamma of P. right? So I'm taking all the points such that we have this inequality right here. And the intersection of all this gives me a fundamental chamber containing this point P. And now I would like to discuss a group theoretical question. So now I found a convex polyhedron, which is a fundamental domain for gamma. How can I find the generators for gamma and defining relations? So our main question, is write gamma as gamma generated by some elements with some defining relations. So these are my generators. And these are my defining relations. Let me start with some simple example. As an example, I will take something like, okay, a dihedral group, right? It will be quite simple. So, okay, maybe the square is too simple. Let us try to do something with the regular hexagon, right? So this is my P. So the symmetry group of P. It's a regular hexagon, right? So the symmetry group of P, it is sometimes denoted as D. I forgot, it's sometimes denoted as dn, right? Or I forgot, or do we write here 2n if it is a 2n sided? Probably we write 2n. Both conventions are quite popular. D sub n. Okay, if it is n sided. Okay, so let us try to follow this. Or dn, or sometimes in, right? It also appears in the, I forgot, or g2n.
No, it's not G. It's
I forgot.
H or something.
It also appears in the classification of the input diagrams. Yeah. Okay, but okay, yeah, please check.
Tell you what it is. Oh no, yeah, it's I2.
Yeah, I2.
I2 parentheses.
N. Right. And I will write that sometimes denoted by, sometimes denoted as D2N. So please be careful. It's just a warning. Okay, so here N is equal to 6, but in fact, we will see that it's a general group. The dihedral group, right? Dihedral group. Okay, let us, so this is a symmetry group of my polyhedron P. And in fact, we can notice that there are the following isometries in this group. We can rotate. So in fact, the fundamental, first of all, we need to find a fundamental triangle. And the fundamental triangle is this. Since, so this is going to be, let me choose this triangle, right? So this angle here, okay, let me write it generally. So what are the angles of this triangle? 2 pi over n, and over 2 again gives me pi over n, right? So this, I don't know, this angle here is equal to this angle here, and this is pi over n. And in fact, we have 2 reflections. So this triangle T, is a fundamental domain. Note that T, this triangle T, is fundamental triangle for gamma. Triangle for the symmetry group of P acting on P itself, right? And in fact, we can observe that the symmetry group of P is generated by just 2 reflections. And these 2 reflections are R1 and R2. Yeah. We see that the symmetry group of P is generated by these 2 reflections. Indeed, a composition of these 2 reflections gives me a rotation. So a reflection allows me to cover this whole white triangle by the 2 copies of my T, right? And then the rotation allows me to get everything. On the other hand, you can see that indeed the fundamental chamber is precisely this, and you cannot make it. I mean, you do not have anything, you don't have any other isometry, basically. So we have only rotations and reflections. And this means that so reflections should certainly bound our triangle, right? It should be the boundary points. So this is a situation of the reflection group. It's quite rigid. And the only, so we need to find now the relations. So some relations are obvious. Reflections are of order 2, right? These are involutions. So I'm writing reflections of order 2, which implies that R1 squared, R2 squared is the identity, right? On the other hand, the composition R1 composed R2 is a rotation okay, it is a rotation around the center at angle 2 pi over n, right? It's a rotation around the center at angle 2 pi over n, which implies that R1, R2 has order n, right? So this element, but written R1, R2 n times, gives you the trivial element in this group gamma, the symmetry group of P. So it is also, and in fact, this is all. We do not have any other, right? We do not have any other. So our symmetry group can be written as R1, R2. So we have 2 generators, right? And R1 squared is equal to R2 squared is equal to R1, R2, and is equal to the trivial element or identity. Sometimes it's denoted by E. So this is my representation, like a group theoretic presentation for the symmetry group of P. Actually, one can change a little bit the generators, obviously. So you can find it's like an exercise, show that this is generated by AB such that A squared is equal to B to the power of N. And identity, right? Is it enough? Yeah, so I can just change. I can take the order.
So that's pretty product.
Yeah.
So product, where is it?
I also probably need AB is equal to BA.
Yeah.
Yeah, they are commuting isometries. Right. Yeah, thanks. So, but no?
One of those needs to be inverse. It's not a group.
Yeah, it's not a commutative group.
Per se.
Let us think. So it's obviously a reflection and a rotation, right? So if I compose R1 with R1, R2, it is just, okay, so this is my A, this is B, right? And this is just R2. Yeah, this is not good. And BA is R1, R2, R1. So it's a conjugation. So and what is it? Yeah, so probably you're right. It should be BA inverse, right? So the inverse will be just the element in the. Oh yeah, so it should be R2, R2, R1. So B inverse. No, is it correct? Okay, so this is R2. I want to get R2. So I should take B inverse A, right? This is my B. B inverse is going to be R2, R1 and R1. Yeah. So AB equals B inverse A. Yeah, now this is a correct presentation. The point is that, so basically the question is how we choose the generators. In this choice of generators, my fundamental triangle is this, and my generators simply move the triangles to the triangle T to the adjacent ones, right? With this choice of A and B, the rotation, it actually moves this triangle not to an adjacent one, but to the one which is next. Yeah, is it correct? So the rotation moves this triangle T, the orange guy, somewhere here, I guess. And the Poincaré method actually allows, so if you find such generators, okay, I will say it the other way around. So if you have already a tessellation of your space by the copies of fundamental chambers, the point is that the isometries that send your T to adjacent chambers, to adjacent fundamental domains, generate your group. So here, these isometries are precisely the reflections R1 and R2. And The Poincaré method basically allows me to get this presentation that I wrote here just from the, I mean, from, in some sense, from geometry, basically. Yeah. Okay, let me move to the second board. So Poincaré fundamental. Okay, I will probably now state the, I will write the general picture. So a general case. P is a fundamental convex polyhedron or gamma. I will even draw some picture. So this is my P. And for every, okay, another condition. I also need one more condition. I want every two fundamental chambers intersect at their common n minus or d minus one dimensional face. This is not always true, but you can modify the chambers in this way. But let me, so a general case, I have this. Let P be the fundamental convex polyhedron for gamma, and assume that every pair of adjacent domains, in fact, these are like gamma 1p and gamma 2p, assume that intersect along their common, codimension 1 face. When, like, where can you get the problem? It can be the tessellation of this type. You see, this tiling of the plane gives you also a nice tessellation. You can take a group generated by translations, and this is going to be a fundamental domain for your translation group, right, acting on the plane. But technically, this face, okay, let me use it in the orange. So technically, this face, it is a face of my P, right? But it attaches to different adjacent convex polyhedra, this one and this one. I will split this into two faces, which are technically sitting in the same hyperplane, but in this case, my P and this one, gamma 1p, they intersect precisely along their common face. Yeah, this is what I want to do. And here, for this choice, yeah, actually, I don't think so. But the point is that, like, generally speaking, you choose any. In fact, you can choose any fundamental convex polyhedron, not necessarily obtained from the Dirichlet construction. Yeah. Yeah, but yeah, I agree. Yeah, I agree. Probably here it's impossible, since basically this is defined by the condition that the distance is less than or equal, then it.
I do have the right picture. These are going to be like, you take your point P, you act on gammas, you get a lattice, then you take more cells about the lattice. That's sort of what you get.
Yeah. Yes. Yeah. Thanks. So indeed, for Dirichlet domain, you do not need this assumption. So we have this assumption, we have this assumption. Okay. Then for every facet F, so this is my facet F. We have a unique isometry that sends P to the adjacent fundamental domain of the tiling, right? There is a unique, okay, for every facet F of P, there is a unique isometry, which I will denote by S sub F, sitting in my gamma, right? Such that SF of P is adjacent to P along F. So their intersection is precisely F, right? It is also obviously a part of the tiling, yeah? Okay, so, but there is another observation which can be obtained from this picture. For every D minus 2 dimensional or codimension 2 face. Okay, so for every codimension 2 face, we have basically a cycle. We have a cycle of chambers. Okay, I should use some notation. Let me use the notation E, since it's analogous to edges in the dimension 3. So I have cycle of chambers. I will call chambers. By chambers, I call the copies of my fundamental domain, right? So these are copies of P in our distillation of the space X. Containing E. Right? It is in this picture, this E is here. It is the origin. So for this point, it is a vertex of my T, right? So for this vertex of T, I have the following cycle. I have many 2n triangles, all containing T. And this cycle, it starts from here, and yeah, like using the rotations, I can like flip these triangles into each other, and at some point I will get back to my triangle. This gives me the whole cycle containing T. This group is finite, and in fact, the cycle gives me this presentation, right? So this cycle gives some. So this cycle is associated to some word as f1 and so on as fn, which is obviously the identity, right? Since I'm getting back to my initial fundamental chamber, and this means that, but I'm using some fact here. Okay, let me check the time. Yeah, okay, I have 5 more minutes, and then we will make a break. So I actually wanted to. Okay, so here I'm using the following lemma. Okay, lemma. If so let it be P and SF P, and somewhere here I have suppose I have gamma P and delta P such that this phase, their common phase is gamma F, right? So if gamma P intersect delta P along the facet gamma F, then delta is obtained from gamma by multiplication on this isometry SF. The only question is what is going first, right? So if I if I multiply this by gamma on from the left side, I will getting delta. So then gamma SF equals an isometry delta, where gamma and delta are the elements from my discrete isometry group. And actually, like the proof is right here, right? I can apply the isometry. What I can do, I can multiply it by gamma inverse, right? I can apply gamma inverse, and this moves to this picture. My chamber gamma P is translated to the chamber P. The facet gamma F is translated to the facet F. And obviously, since gamma P and delta P were adjacent along gamma F, delta P should be translated, it translates to SFP, right? But this implies that, so basically proof, apply gamma inverse and see that gamma inverse delta P is SFP. And this finishes the proof, since for chambers, it is a very nice thing about tilings, right? So if you know that some isometry maps, okay, so if you know that for some isometry, gamma P is equal to delta P, then gamma and delta coincide, right? This is the definition of tessellation. Yeah, so every orbit has a unique representative in the interior of my P. Yeah, so this basically allows to use this simple trick. So this shows that actually so in fact, this shows that every gamma, so as a corollary, every gamma from a group gamma is a composition of some right, of some generators, of some side pairing transformations. So let me call it as a side pairing. Where should I? Okay, I will write it down as here. It's a unique isometry, it's F, and these are usually called side pairing isometries or transformations. So these are SF, are side pairing isometries. SF. And so this implies that every element, so it's a corollary, gamma is generated by SF for all F facet of P, right? And then look, getting back to the cycle, we know that every chamber in this cycle is some, also is some word. But in fact, we just do, I don't know, let me try to draw a picture somewhere here. So we have a, okay, basically just look here, right? So this isometry, this triangle is R1 of T, right? Then this triangle is, okay, it's a little bit tricky. So what's going to be? It's going to be R1, R2 of T, right? So this one is, yeah, is it correct? So if I first apply R2T, I'm getting here, but if I then apply R1, I indeed switch to this one. So I'm adding a new generator from the right side. If I go along, if I go like counter clockwise, yeah, I think it's okay. So this is going to be R1, R2, R1, T, and so on, until I'm getting back to my initial triangle T, which gives me R1, R2, n times being equal to the identity, right? And so, yeah, this is, this all is based on this lemma, basically, and on the, so the Poincaré fundamental polyhedron theorem, in fact, says that it is enough. So let me just state this theorem, and we will make a break. Poincaré fundamental polyhedron theorem says that gamma is generated by all SF. Okay, so I will carefully write that it is generated by the set SF. F is a facet of P. And we have two types of relations. So the relations SF as F prime is equal to the identity, and all cycles around, so and all cycles around codimension 2 spaces. I didn't tell you what is the first relation, but the first relation comes from here, just from this picture. So if I have a P, sorry, an F, my face, and another chamber SFP, F prime is a facet that goes that is mapped into F by an F. So here F prime is defined as, okay, what is it? It's just a preimage of F, right? It is basically a facet of P, which is SF inverse of F. So this is precisely the facet F prime that is sent to F by an isometry SF. So my S F prime of P is here. And these are the elements. So in fact, one can simply see from this picture that indeed SF inverse is SF prime. Yeah, it just follows from this. And so we have two types of defining relations. SF and SF prime should give us a trivial product, and all cycles should be trivial. A space X? Yes, yeah. Well, I am thinking about just something pretty good, like homogeneous spaces, like hyperbolic spaces, Euclidean. Yeah. In fact, yeah. Yes. I consider mainly hyperbolic spaces, since there we still have the fact that hyperplanes are indeed totally geodesics, while in the general, like in the broader case, in fact, the set where we have the equality here, right? Like the bisector, it's not a totally geodesic, actually, like in general, right? So in general, fundamental domains of discrete groups are not bounded by totally geodesic hyperplanes. So like for simplicity, so far we consider like hyperbolic spaces, and it's good. Okay, yeah, let's make a 10-minute break. Okay, so let us continue our lecture. I stated the theorem that a group gamma is generated by side pairing isometries, and with those relations, with those defining relations. But in fact, some sort of converse is also true. I'm not going to like give it in all details. I will just write down that in fact the converse is also true if P is a finite-sided convex polyhedron, and okay, and there exist isometries, okay, S1 and so on, Sn. So if it is finite-sided, let us assume that capital N sided, such that S1 be Sn be R So they are not overlapping convex polyhedra, right? Are not overlapping polyhedra, and for every so this is E, F, and this is P, and so for every codimension to space E of P, we can find a cycle of chambers, right? We can provide a cycle of chambers. So the cycle of chambers all containing E, right? So a cycle, let me write it this way, as I1 of P, as I1, as I2 of P, and so on, as I1, as I don't know, K, as IK, P, all containing E, then and I go to the next board. So then the group generated by this with those defining relations gives me a discrete group of isometries with fundamental polyhedron P. Then the group gamma generated by S1, Sn is a discrete group with fundamental polyhedron P. In fact, this is, if I'm not mistaken, this is not 100% correct. There is some condition about cusp points, maybe. I think I will, I'm not sure. I will just recover it right now. But probably so if this polyhedron has some points infinity, generally speaking, it is not necessarily finite volume, or it is just finitely sided. So it may have cusps or something. Probably we want these isometries somehow separate the neighborhoods of cusps, but I'm not pretty sure. I don't remember, unfortunately. But I will just leave a remark that there is some extra assumption on on vertices, on vertices of P. So to make it work, make it at 100% correct. But for, say, reflection groups, all is fine if you have a Coxeter polyhedron. So as a, say, as a corollary, So if P is a Coxeter polyhedron, that is, all dihedral angles are, I will just remind, so all dihedral angles are of the form phi over some integer mij. Then the group generated by reflection is discrete, by reflections in the walls of P is discrete, and P is its fundamental polyhedron. So then the group, which I will sometimes denote by this, REFL of P generated by reflections in the walls or sides or facets of P is discrete with P a fundamental domain. In fact, generally speaking, it's not that obvious. You can say you can just draw it, I don't know, a triangle with angles pi over 5, pi over 7, pi over 11. Go ahead and try to prove that the group generated by reflections will indeed tessellate the entire space, right? And that this triangle will be, well, it's like after you prove that you obtain tessellation, it's already clear that this is indeed a fundamental chamber. But generally speaking, it's not like that obvious. But once you have the nice angles, you can apply this method. You can get all cycles around vertices of your triangle, right? And you definitely have, after reflecting this Coxeter triangle, you definitely have some triangles adjacent to your given triangle. So after you have all, so in fact, this theorem kind of gives you a subtessellation of some piece of plane. And this theorem tells you that if this subtessellation is nice enough, then you can recover the tessellation of the entire plane, right? So it's like, yeah, it's like on this picture. So in fact, like for the square, this theorem basically tells you that you need to have, okay, I do not have a good picture. Let me redraw it here. So the picture will be, in fact, like that. Suppose you take a rectangle, right? In fact, what you need is to choose this rectangle, P, and then you need altogether 9 guys, right? You need this. Okay, for adjacent, and also for every vertex, you need the cycle around this vertex. And this theorem basically tells you that, okay, getting 9 copies of P is enough. Well, the identity 1 plus 8 different. So yeah, this is pretty nice. And yeah, in fact, this method is indeed quite broad. So if you have some nice polyhedron, and you indeed found isometries. So what is important that these elements over here are isometries, right? So these are just some isometries that do this subtessellation. Then the group generated by this is discrete, and then you apply the initial Poincare fundamental polyhedron theorem to find out that actually you have all relations. Okay. So now, yeah, let me state one more important theorem, and I think we will discuss some dynamical aspects of groups. Okay, so let me tell you that if if gamma is a discrete group, then we say it's cofinite if the volume of the fundamental chamber is finite, and it is co-compact if the fundamental chamber or the fundamental domain is compact, right? So in fact, the following theorem is true. Okay, if assume that here X is the Euclidean space, the sphere is D, or the hyperbolic space HD. In fact, it is also true for some other class of relatively good spaces. So if gamma in isom X is a cofinite discrete group, cofinite discrete group, then, well, then P is a convex hull. Okay, then P can be chosen to be a convex hull. So let me write it more precisely. So then P, the fundamental chamber, yeah, then a fundamental convex polyhedron P of gamma is a convex hull of finitely many vertices sitting in X or on the boundary of X. So a finite number of vertices and belonging to X or the ideal boundary of X where the letter is defined, right? I mean, in some cases it's just trivial. And belonging to the actual ideal boundary of X.
So when you say cofinite, do you mean cofinite volume or cofinite?
Yeah, it's cofinite volume, yeah. So by cofinite, I mean that the volume of the fundamental chamber is finite. Yeah. So the volume of X naught gamma is finite, right? Okay. And I will actually leave a remark belong only to X when gamma is co-compact, which means that X mod gamma is compact. Moreover, gamma is then finitely generated and even finitely presented. Finitely generated and infinitely presented. So the number of, in fact, of those defining relations is finite, right? So this is a very important theorem. It is, well, I would say that it mostly follows from that, but probably some extra considerations are needed. Okay, so we see we have the following nice interpretation of cofinite or compact discrete groups. First of all, we have that fundamental chambers are pretty nice convex polyhedra. As I showed you in the case of discrete reflection groups, these polyhedra have relatively nice combinatorial and geometric properties. In fact, something more is known about Coxeter compact or finite volume Coxeter polyhedra in higher dimensions. Probably I will mention this a bit later. As for compact Coxeter polyhedra, for instance, it's known that they are simple. Every vertex belongs to precisely D hyperplanes, D facets of codimension 1. But this is only for compact case. In the non-compact case, it is allowed to have vertices of higher valence, but the point is that it's still quite there is quite concrete list of cusp possibilities. So again, we'll discuss it a bit later. But what is important that fundamental polyhedra have finitely many facets and vertices, and this gives you finite presentation. So you have finite number of generators, and this method allows you to obtain certain group theoretic presentation of your group. Definitely, this is not the minimal presentation, right? Geometric presentation is generally quite far from being minimal. And a good example is actually a reflection group. You can think of, say, a symmetry group Sn. It is generated by involutions, right? By just transpositions. And those can be viewed as reflections in hyperplanes in D+1. Okay, so if it is a group SD, then you can think of reflections in hyperplanes in D+1 dimensional phase. But the minimal, as I remember, number of generators is just 2. You need 1 cycle and 1 transposition, if I'm not mistaken. Yeah. So you see the geometric, yeah. Yeah.
1, 2, and 2.
And you get everything, yeah. So geometric presentation is generally, so I just want to fix this thing, right? But still, it gives you something. It still gives you something if you find some. So if there is some way to find some, like I don't know, like a minimal number of convex fundamental polyhedron with minimal number of facets, it gives you some bound on the number of minimal generators. It will be the lower bound, but it's still something. So we see there is some connection, and these methods are useful. Okay. In fact, I promised you to discuss some dynamical aspects of group actions, and so we are mainly interested in finite covolume discrete groups or co-compact discrete groups. So the question is basically how to detect those groups. In fact, there are many sides of this general picture, and we will try to see how can one detect those groups from the other viewpoint. So now, dynamics of discrete group actions. This is my next topic. Okay, let's go here. So dynamics of discrete group actions. And in fact, this usually means that we want to have some wild behavior of orbits. In particular, we want probably to have dense orbits, but we discuss discrete groups. So dynamics of group actions means basically the study of of dense orbits. In the space X itself, orbits are discrete, but we already discussed, right? We already considered the case of elementary groups where we have some accumulation points at infinity. Okay, so now I want to define the following interesting notion. I want to define that, so let gamma be X a discrete group. And and let suppose we have a boundary. Then a point, okay, a point, I don't know, P from the boundary of X is said to be a limit point if there exists a point X in X and a sequence of gamma n of elements in gamma such that gamma n X converges to P as n tends to infinity. This notion of a limit point, in fact, can be given for a pretty large class of discrete groups and a pretty large class of groups acting in a really large class of different spaces, metric spaces with some conditions. So this boundary, there are several notions of boundary, and this is actually a pretty large theory. I'm not going to delve into the details. So for us, X is just a hyperbolic space. So otherwise, it would be just really a year-long course and pretty advanced. So for us, I'm leaving a remark. So for us, X is just HD. It's the most interesting case in the framework of our course, but it can be generalized to many spaces, right? But this can be defined in many, really many spaces. In particular, one can consider Gromov hyperbolic spaces. Okay, then I will use the following notion. So this is a limit point, right? So I defined a limit point. Now I want to define the limit set. So this is a limit point. And the limit set, of gamma, I will denote it as lambda gamma, is the set of all limit points of gamma. And this is a very important notion. So obviously the limit set is a subset of the boundary, which is d minus one dimensional sphere, right? So this is what we have in this case. Okay, so you see, it tells you that you need to take all the limit points. But the following is actually true. So let me state the following theorem. Lambda gamma is in fact equal to the closure of any orbit of the space. So it is the closure of any gamma x. Well, I need to intersect it with the boundary. Okay, I will not use d here. And it is true for every x in x. Let us try to prove it. And again, I'm proving this in HD. So suppose I have an orbit, and suppose I have some limit points from lambda gamma. So let P be the point from the ideal boundary. Okay, so let P be the point from the ideal boundary such that P doesn't belong to the limit set, right? And let Q be the limit as n tends to infinity of some gamma n x for some x in x, yeah, such that Q is not P. Any gamma, right? Yeah, any gamma. So yeah, let gamma be just any. I will even write it here that it is any discrete group. So the point is that you can just choose one convenient point, right? And take the orbit closure at infinity, and this will give you the lambda gamma. Yeah. So, okay, the proof is going to be a little bit sketchy since I'm afraid I will be running out of time, but maybe, okay, let's try to make it as rigorous as possible. In fact, there are a couple of different approaches to this question, but consider the upper half plane model, upper half space. And set one of these points to be at infinity. I'm just trying to think which is more convenient. So the question is that if we have a like convergence to some element, then at some point they will, okay, and then set P. Okay, so P is my limit. So and set Q is infinity, and then P is not Q. So which means that P belongs to the real line, right? Oh, okay, it belongs to the hyperplane. So it belongs to the hyperplane xd is equal to 0. So we have such a picture, right? We have infinity Q at infinity, and we have some P on the boundary, right? And so we have, so assume that okay, so Q belongs definitely, so this belongs to lambda gamma, right? So we assume that okay, wait a second. So P, what I'm trying to show, I'm trying to show that Q okay, sorry, I think I a little bit confused myself by this notation. So I'm choosing 2 points. One is from my lambda gamma, one is from the closure, right? So I'm taking this point P, which doesn't belong to lambda gamma, but it belongs to the orbit closure, right? So this means that my point P, so let me take it, so let it be P here, sorry. This point P doesn't belong to lambda gamma, but it is the limit point of some orbit, right? No?
That's, so if you're the limit point of an orbit, you're definitely in lambda gamma by definition, right? What you want is the problem points are potentially points that are in lambda gamma, but are not in the orbit closure of our one particular X. So there's some other point that does converge to it.
Yes.
X shows it.
Okay, yeah, so actually here it should be belongs to lambda gamma, right? So suppose that I have a point which belongs to lambda gamma, but and Q is some limit point for some X, and Q is not equal to P, right? So this is the correct statement. So I found some point on the boundary, which is generally some limit point, but not the limit point of my concrete orbit, right? So then I consider the upper half space model, and I set 1 point, I put 1 point at infinity, and definitely since P is not equal to Q, we have that this, right? So in fact, I wrote it a little bit uncarefully. So, and we said, since I should write here the dot, right? Period, since P is not equal to Q, we have that P belongs to the horizontal hyperplane at the level 0, right? Okay, now I will remove this. And I'm going to use the board over here. Okay, now I'm trying to, I will basically get the contradiction, since if P is the limit point, right, I have the following. Since P belongs to lambda gamma, there exists some point Y and in UD and a sequence of, I don't know, gamma K. By the way, this wasn't a good idea. So I was trying to show that, okay, so since P is the limit point, then there exists a sequence of, I don't know, gamma n prime, such that gamma n prime P converge to, sorry, gamma n prime Y converge to P, right? Okay, so I have, geometrically, I have something like that. I have a number points, I have a sequence of points Y. I forgot, P is my, oh no, P is infinity, no, P is here, right? So I have Y, and they converge to this point P here, gamma n prime Y, right? And on the other hand, I have, this is P, this is Q equals infinity, and I have some gamma n X that converge to, I actually need to switch to the same sequence, right? So in fact, I don't, yeah, I don't think I need this. Yeah, I'm trying to show that if the point is a limit point of some, so basically I want to show that if I have two sequences of some, okay, I have one sequence, but two different points, they should converge to the same orbit. Oh, sorry, to the same limit. Yeah. So the desired theorem would follow from this. So the desired theorem would follow from this. If gamma n, okay, if gamma n X converge to P and gamma n Y, so then gamma n Y also should converge to P, right? So then converge to P. We assume that it is not true, then but this implies from the following. This implies from the fact that the distance between, so the distance between gamma I, okay, gamma n X and gamma n Y is equal to the distance between X and Y. And on the other hand, so I cannot have like two different limits, because at some point I will have just really different d-coordinate. I basically can measure the convergence by the level, right? So I can measure the convergence by the coordinate with number d. And I will just see that at some point they will go in. I mean, they're separated from each other. And this is the contradiction to this equality, right? They will just be too far from each other, but they cannot be too far. They are hyperbolically, they are at the same distance between each other. Yeah. So I cannot even converge actually to the same. I cannot converge to two different points here, but it's just a bit easier to see in the upper half space model. Okay, maybe it's a little bit too sketchy. I think we can try to work out the details in the next lecture. But this is indeed how it goes. So if I have a, if I have a limit point for some gamma n, right? Then I will choose the same sequence for x and show that it should converge to the same point. And it goes this way. If one is, say, 0 and here it's infinity, then you cannot have two. So in fact, here we will have the same sequence of elements. Yeah. I do not need the second sequence. I basically need to take the same sequence, and I need to show that they converge to the same point. If they converge to different points, I don't know, I chose y somewhere here and x somewhere here. So this distance is fixed, right? But if they converge to the same point, then gamma n x is like, it goes closer and closer to infinity. Gamma n y goes closer and closer to this hyperplane. Then this distance, right? It's getting larger and larger. So gamma n x, and this is gamma n y, right? Yeah, so I do not need, in fact, I don't need gamma 1 prime. So what I'm trying to say that, yeah, if I found the limit point, okay, so this gamma n, it actually comes from what sequence? Okay, yeah, so I have the point that belongs to lambda gamma. So in fact, I want to write down that P is the limit of gamma n y, right? So P is the limit of gamma n y, and then I'm taking the sequence of gamma n x. I'm trying to show that the I mean, I cannot have a subsequence converging to, in fact, it's not like very careful. I, in fact, passed the subsequence, but after passing the subsequence, I can assume that I work with the same sequence gamma n, right? So after I pass to the subsequence, I assume that gamma n x converge to infinity, gamma n y converge to something on the hyperplane. The distance between x and y is some fixed number, but gamma n x, gamma n y, the geodesic segment has the same length as this one. But when one goes to infinity, another one goes to the horizontal hyperplane bounding the upper half space model, this cannot gonna happen. How to see this? Just look at the metric formula. Yeah, we have the concrete metric for the distance between the points in the upper half space model. It is just cosine of distance is equal to 1 plus something, and you will see that it cannot happen. Yeah, it cannot happen that the difference between the dth coordinates is larger and larger. So that's the end of the question. Okay, so in fact, we will, so in the next lecture, it's going to be next week. Yeah, I just reminded, there is no lecture this Thursday. Yeah, it was in some emailings, but I will remind about that. Yeah, I will definitely remind about that. So next Thursday, we do not have a lecture, but next Tuesday, we will continue discussing the properties of limit sets. Just a short spoiler, if gamma is cofinite, then the limit set is the entire boundary, the entire sphere on the at infinity. So in the cofinite or co-compact cases, the limit set is the entire sphere. Another interesting property of lambda gamma is that is actually, okay, up to some in non-elementary case. In non-elementary cases, lambda gamma is a minimal, it is the minimal closed gamma invariant subset. In fact, from this theorem, we already see that it is a closed subset of this sphere, right? And we also see that it's definitely gamma invariant, right? This theorem basically implies that lambda gamma is gamma invariant. But it turns out actually the stronger statement is true. It's the minimal gamma invariant closed subset if it is not finite, right? So if it is infinite, then it is an important condition. And then we will prove and just, yeah, and we'll just write down some interesting properties of that. Okay, thank you for your attention and see you next week.